Okay, welcome back everyone. So today is going to be the last discussion hour of this course. And what we will do today, so the idea is, so just for a quick recap of what we did is like we derived something called as the Rayleigh stability equation, which assess the stability of inviscid parallel flows or nearly parallel flows as we saw it in the past two sessions that we conducted. So in principle, what we use it. So the idea as so how we actually approach this problem is like so we introduce certain perturbations to the base states, and then we try to look how these perturbations evolve with time by using certain things known as so in principle we use the linear stability analysis regime, which mandates the fact that the magnitude of the perturbations are less than the magnitude of the base state variables, and we use something called as the normal modes. For example, assuming that the perturbations, if they grow or decay, they will show an exponential, so they will precisely evolve exponentially. Okay, but so within this, within the regime of linear stability analysis and using normal modes, we eventually found out that expression which governs how the perturbations will, if they exist, will die down or grow with time exponentially using a single ordinary differential equation, which you can see on your screen, and we have spent you know some substantial amount of time trying to derive this from the first principle, of course. And you can see that it's rather so out of all the maths that we did, you see that inevitably it's an eigenvalue problem that we are actually trying to solve, because we saw that. So this so what makes it a eigenvalue problem is, you can see that the quantity that we are trying to calculate, that is phi and c, this c happens to be the eigenvalue and phi happens to be the corresponding eigenfunction. And as I said, what makes it an eigenvalue problem is, you can see that phi equal to 0 satisfies the equation trivially, which means that there exists a trivial solution. And we saw that the boundary conditions that we derive for phi, they are also homogeneous. So homogeneous governing equations and homogeneous boundary conditions are kind of a perfect recipe for an eigenvalue problem. Okay, so so I'll not show you how to solve this problem. So there are multiple ways of solving this problem. One way is, of course, you can resort to numerical methods for solving for phi, where you can discretize this equation in spatial space, and then solve for phi, because remember, phi is just a function of z. Okay, so for example, d2 phi by dz2, you can just discretize this as something like phi of I plus 1 minus 2 phi I plus phi of I minus 1, and so long and so forth. So you can basically use finite difference in principle, what I'm trying to say, in order to solve this problem. Okay, but so I'll not show you those steps, okay, because this is actually beyond the reach. One second. This is actually beyond the reach of this course. As far as this course is concerned, we are actually more interested in the fluid dynamics part. So but yes, there are multiple ways of solving this problem. So there is something also known as spectral method. So you can also use spectral methods here to solve this problem. There are multiple ways of doing of solving these kind of stability problems. Okay, so what we'll do today is, like I said, that how can we, so instead of actually trying to find out the solution of the Rayleigh stability equation, what we'll do is, we'll actually try to understand that how the Rayleigh stability equation can be applied to assess the stability of a given base flow. Okay, and we'll look into one of the instances, or one of so so, so the proper word that I should say is, like, we will look into one of the criterias which can be used to assess the stability of a given base flow, that can be drawn, the idea of which can be drawn from the Rayleigh stability equation. Okay, so the question that I pose here is something like this. So the question is, how does Rayleigh stability equation oops, sorry. So how does Rayleigh stability equation predict about the stability of a given base state. Okay, so I hope things are clear from the question itself. That so in principle, what we are trying to see is how can we apply the Rayleigh's, the Rayleigh stability equation to assess the stability of a base state. Okay, so for that there is a criteria which is known as so this is a very famous criteria. This is known as the Rayleigh inflection point criteria. Okay, and I'll not show you the proof of this criteria, but the proof of this criteria comes from the Rayleigh stability equation itself. Okay, so you can use the Rayleigh stability equation to prove the Rayleigh inflection point criteria, and that's how and that's how this criteria can be used to assess the stability of a base state. Okay, so what this criteria says is uh, a necessary condition, and I highlight the word necessary because it is not a sufficient condition to be absolutely sure about the nature of the perturbations, but it's a necessary condition that needs to be satisfied. So it says that a necessary condition for instability is that the base flow profile must have an inflection point. Okay. So I believe you guys know by the word inflection point, it just simply means that if I have, so for example, if I have a base flow, which is capital U of Z, if this is my base flow, okay, and if there exists an inflection point Z naught, for instance, Z naught is my inflection point, then somewhere within the domain, my U double prime evaluated at Z equal to Z naught has to be equal to 0. Okay, this is what the Rayleigh inflection point criteria says. Okay, and by the way, I have not shown you the formal proof of this Rayleigh inflection point criteria, but the proof of this, as I have said, this comes from the Rayleigh stability equation. Okay, so in fact we don't have much time to discuss the proof, but yeah, so this is how, since the proof comes from the Rayleigh stability equation itself, this asserts the fact that indeed you can use the Rayleigh stability equation to predict the from a given profile to predict whether the base profile is stable or not if you add certain perturbations to it. Okay, so I'll just show you a very quick example. So let's consider that my given base flow is a Couette flow. Okay, which means that so if it is a Couette flow, okay, it basically means that my profile is proportional to Z, because that is how Couette flows are designed. For instance, I can tell that U of Z is some, let's say Z by H. Okay, where you can some C times Z by H, where C is a constant, that doesn't matter actually. So if this is if this is my base flow, which is a Couette flow, as you can see, okay, then the Rayleigh inflection point, then let's see what the Rayleigh inflection point criteria says about the stability of this base flow. Okay, so if I calculate what is U double prime, so U double prime of Z simply comes out to be equal to 0, regardless of which point we are looking at, because at each Z naught within the domain, at each Z within the domain, in fact it says that each point is an inflection point. Okay, which basically means that by Rayleigh inflection point criteria, by Rayleigh inflection point criteria, Couette flows are unstable. Okay, so it appears that if you apply Rayleigh inflection point criteria, it says that Couette flows are unstable, but there is a catch. So remember I said that the condition, or the Rayleigh inflection point criteria is a necessary condition but not a sufficient condition. So there is one more criteria that you need to use, although I'll not formally prove this criteria, it's just for a know-how that I'm saying. So there is something known as the Jortov's criteria. Okay, I think I wrote. Okay, so it's Jortov's. So it's JYOR, I think it's something like that. TOFF. It's something like this. I forgot the spelling, so the criteria is basically the Jortov's criteria. So the Jortov's criteria. So if you use the Jortov's criteria, although so the Jortov's criteria is a, yeah, I think it is, spelling is something like this. To the best I remember. So it is, so there is an F here. F is usually silent, and it is something like this. Yes. To the best I remember, this is what Jortov's actually spells as. So, so although the Jortov's criteria is also not a sufficient condition to assert the stability of the given base flow, but the Jortov's criteria is a more stronger criteria than the Rayleigh, inflection point criteria. And by Jortov's criteria, you can say that Couette flows is, so if you have, so I'm not showing you the Jortov's criteria, but if you apply Jortov's criteria just like how we applied Rayleigh inflection point criteria, you will see that Couette flows are essentially stable. Okay, this is what the Jortov's criteria says, which means although the Rayleigh inflection point criteria states that Couette flows are unstable, but the stronger criteria, which is the Jortov's criteria, if you applied it, you will basically see that Couette flows are stable in nature, which means that if you add perturbations to a given base flow which bears the signature of a Couette flow, you will see that the perturbations will eventually die down. Okay, so there is one more criteria which is known as the Howard semicircle theorem, and I would say it is even more stronger than the Jortov's criteria. So eventually you need to check that the Howard semicircle theorem is it's called the Howard semicircle theorem. Okay, so you basically need to check. So what it says is that for stability, your eigenvalues should lie within a semicircle. That's what that's what the Howard semicircle theorem says. Although, and again, I'll not show you the formal mathematical expressions and proof here, because we don't explicitly need that in this course. So if you're interested, we can discuss this you know in the discussion forum itself. But yes, so as I was telling, just be familiarized with the name. So this, I would say, is the most strongest of the criterions that we have studied. Okay, so after you check Rayleigh inflection point criteria, it is necessary to check the Jortov's criteria, and after checking the Jortov's criteria, you need to check that if the eigenvalues lie within the semicircle as described by the Howard semicircle theorem. Okay, again, I will not go into the nuances of these things, so I just brought it up just for a know-how kind of things to uh, so so the objective is to just show you that how Rayleigh stability equation can be used to predict the stability of a given base flow. Okay, for this, these criterions are designed, and you need to check that which criteria is satisfied or not precisely, okay, in order to assess the stability. Okay, so this ends formally on the stability of inviscid parallel or nearly parallel flows. We have spent substantial amount of time trying to understand it, trying to derive. So we looked into every nuance bit of this derivation, like starting from the fundamental equation, non-dimensionalizing it, applying linear stability analysis and normal modes and so on and so forth, to finally get the expression of Rayleigh stability equation. Okay, and I believe that is clear to everyone. uh, I repeat again, what you were shown in the lecture series is that you were derived something called the Orr-Sommerfeld equation, and Rayleigh stability equation is a special case of the Orr-Sommerfeld equation when your Reynolds number is equal to 0. Okay, or in simple words, Rayleigh stability equation is used to predict the stability of inviscid flows, whereas Orr-Sommerfeld equation is used to predict the you know instability, or it's used to predict the behavior of the perturbations for viscous flows. So Orr-Sommerfeld equation, I understand it's more general, and in fact the Orr-Sommerfeld equation is fourth order in nature, and as we have seen, the Rayleigh stability equation is actually a second order equation in nature. It's a second order ODE. Okay, so this finishes the discussion on this aspect. So before doing a formal recap of, so as I said, today's class is just a recapitulation of what we did. But before doing this recapitulation, what I felt is that I think I should discuss some physical, how other instabilities also kicks in, because we just looked into a very specific example of an instability, that is like the instability of parallel flows, and you have also looked into something known as the instability of viscous parallel flows. But these the vast literature of instability is not just confined into these parallel and inviscid parallel and just viscous parallel. So there are a lot more to it. In fact, I would say that these two are just the tip of the iceberg in studying instabilities. Okay. So I will just discuss. So again, I repeat, I will not, go into the formal mathematical proof of this and the formal, you know, I mean, I'll not derive anything, but I will show you certain other examples of other, and I would say they are very interesting examples of instabilities that occur in nature. Okay, and they are very different from the instabilities that we actually studied. Although you can do a linear stability analysis and things like that, but understanding where from these instabilities come from, I feel is essential in order to get a little bit more broader perspective on hydrodynamic instabilities. Okay. So then the question that I pose is that what are the factors that causes instability? Because if we want to learn instability, we should first question ourselves that what actually causes instability. Okay, because see, remember in the problems that we solved exclusively, we don't actually question that where from the perturbations actually came, because we just say that there is a base state and we add some perturbations, but where from these perturbations come is another ball game. Okay, and that and I'll just like to give you a preview of the things that can actually bring in instability into a fluid system. Okay, so one of the factors, so maybe I'll write factors responsible for instabilities. Okay, and one of the factor that is you know widely regarded as a as a factor for causing instabilities in fluid systems is body forces. Okay, and by body forces, the first force I think it come into your mind is gravity. Okay, so then we'll see that how gravity can cause instability in a fluid system. And one of the classical example of gravity causing instabilities is a very famous instability problem. This is known as the Rayleigh-Bénard convection. So I'll give you the physical picture of the Rayleigh-Bénard convection. Okay, okay, so let's try to understand that how gravity causes instability through this classical example of an instability problem, which is known as the Rayleigh-Bénard convection. It's named after Lord Rayleigh and Bénard. Bénard, I believe, is a French physicist, to the best of my knowledge, and we will see that how this Rayleigh-Bénard convection actually works. Okay, so imagine we have a beaker, okay, and we fill the beaker with some fluid. Okay, so we have a beaker and we fill the beaker with some fluids. Okay, and we are assuming that as of now, so what we are assuming this is the following. As of now, this is so there is just only a single phase that is present, that there is no solutes that is present inside the fluid, and it is just the fluid itself or the solvent basically. So now what we do is, so this is a well-behaved system. Okay, we know that if you have a beaker and you put in fluids inside the beaker, or you just fill the beaker with water, we know that it's a very nice stable system and the water is not going to cause you any problem there. Okay, but the problem comes, let's say, when we heat the beaker with let's say with let's say by a fire, or fire is not so good. Maybe I'll draw the fire in this. So by a flame, let's say I'm putting the beaker on a stove. Okay, let's say I'm putting the beaker on a stove. Okay, and so this is where I'm putting my beaker, and I'm heating the part of the beaker with a candle. Okay, now this is where things get interesting. So you need to understand that when I heat the beaker, and when I heat the water that is inside the beaker, okay, with a candle, so what this candle is doing is it is creating localized heating in let's say this region. Okay, so if I now look into a fluid element in this region, okay, what I will see is, then if I then plot, okay, maybe what I'll do is I'll name the axis. I think that's better. So let's say this axis is my z axis, okay, and the other axis you can consider it anyway in x or y. That doesn't matter here. Okay, so now if I pick a fluid element and then I plot the temperature distribution, okay, as a function of z. So what I'm doing is I'm plotting Tz versus Z. That's what I'm doing. So I know that since there is a candle which is locally heating the fluid, initially at the bottom, I know that at the bottom, okay, let's say my temperature is somewhere here. Now I know that this temperature is going to decrease when I go, when I go into a when I increase the height, basically when I go along the plus z axis. That's what I'm saying. That's obvious, right? Because the heating is at the bottom, so when I move up, I will sense that my temperature is going down. So this is how actually my temperature will vary, okay, inside the beaker. And you can lay, let's say so this temperature distribution is, let's say, for this cross section. That's what I'm. So let's focus on this cross section itself, because you can have a different temperature profile for a different cross section, but let's focus on the cross section where there is heating. Okay, all right. Now if I draw, or if I map the corresponding distribution in density, I know that where the temperature is higher, the density of the fluid element is less, which means the corresponding variation is then in density is going to look something like this. Okay, this is what the corresponding variations in rho of z, which is the density of the fluid as a function of z, would look like after I heat the beaker. I mean, provide heat to the beaker from this candle. Now it's obvious that the fluid element that is here, will be less dense than the fluid element that is present over here, which means this fluid element will try to move up. Okay, and this is very important, you need to understand. So this fluid element will try to move up owing to the fact that it now have a density which is less than the density of the surrounding above fluid. Okay, so this fluid element will move up, it will go up. Okay, so this element will move up because of the difference in density, and it will try to reach into a state where it can equilibrate with its surrounding. But since this fluid element has moved up, there is actually a gap that is being created because the fluid here has moved above, which means this gap, so this difference in density, or it's like you can equivalently say the difference is buoyancy, has introduced or induced a pressure gradient, which will be which and since it has induced a pressure gradient, this will then drive a flow from the top towards this side. So I hope you can now understand that the fluid will move up. Okay, the fluid will basically move up because of difference in densities or difference in buoyancies, which will then drive an induced pressure gradient, which will take the fluid from the side and try to fill up this gap. Okay, and then you can sense that when this particle reaches above, you see that its density will then increase, and then it will see that, okay, I cannot reach here anymore, so this will again then try to come up with through the path. So you see there is a circulation cell that is being developed. You see there is a circulation cell that is being developed, and these circulations, these are known as Barnard cells. Okay, these are known as Barnard cells. Okay, so this is how and as time go on, you will see that more and more Barnard cells are being formed. For example, more and more cells will be formed. Okay, and these things, and this is how the instability is kicked in, and this is how gravity actually determines a role in creating instability in fluid. Okay, and this example that I have shown, this is known by the name Rayleigh-Bénard convection. Okay, now I hope this is clear. I hope that the concept of Rayleigh-Bénard convection is clear. Okay, now there is one more instability which I feel is even more interesting, and this is like adding some complication into the Rayleigh-Bénard convection. Now try to answer this. So this goes by the name double diffusion instability. Okay, now what is then double diffusion instability? So you can understand double diffusion in instability from the Rayleigh-Bénard convection itself. But now what you do is, in double diffusion instability, with water you add some salt. Okay. So now if you have a salt and water system, this is classical example of where you see a double diffusion instability. Then what happens? Let's try to understand. I have I have my beaker, okay, and I have water in my beaker, okay. Okay. Now what I'm doing is I'm heating just what I was doing before. I'm heating this with a candle, okay, providing some heat, okay. But now instead of it being a clear water, I add certain salt in the beaker. These are my, let's say, salt particles. I know that salt is insoluble, but just for a representation, I'm sorry, salt is soluble in water, but just for a representation, I'm just showing it like this. Okay, so these are salts. And you can just think of it like an ocean water. You are filling a beaker containing ocean water. That's it. So now, and even more interesting things happen. Okay, so try to understand that salt, a mixture of salt and water is heavier than pure water, which means in when I don't have, when I don't basically have this heater, if I add salt, I know that my salt is going to settle at the bottom. That is obvious, right? But the problem comes when I heat this beaker. So now I know that the salt has the tendency to settle at bottom, but I equivalently know that there is heating at the lower end of the beaker, which means that the fluid will try to move up. But the salt that is present will also try to hold the fluid down because it have a higher density than the bulk fluid which is at top. So now there is a competition. It is not that these Barnard cells would not readily develop because I have salt in the beaker. Okay, so at the bottom, since the salt concentration is more, we will see that at the bottom, I repeat, the salt since the salt concentration is more, salt basically, the concentration of the salt basically overpowers the effects of change in density, which means that at the bottom my fluid will remain stable, but when I move up, I know that my concentration of salt will decrease, which means that the temperature effect will then flow in, then kick in, and it will then start developing these Barnard cells. Okay, but now try to understand that these Barnard cells will try to develop not from the bottom, but after a distance, let's say h star, and this distance is where the effect of salt is less while the effect of temperature is more. So this problem involves actually two diffusivities. One is the thermal diffusivity, okay, and one is the molecular diffusivity, which is the moment of the molecules. And I know that at the bottom, in this region, I know that my molecular diffusivity actually dominates. Okay, it's not actually correct to say, because the magnitude of thermal diffusivity is very much higher than the magnitude of molecular diffusivity. But at the bottom, since the concentration of salt is more, this so since the concentration of salt is more at the bottom, salt actually stabilizes the system there, even though there is heating. But as we move up, basically as we move up, I know that my concentration of salt is less, and and thermal diffusivity coefficient is much greater than the molecular diffusivity coefficient, which results in which results in creating a flow that will now move up after a certain, let's say, h star. After a certain, let's say, h star, so this will move up and then create this recirculation, Jones order Barnard cells. Okay, so this is what happens when you have a solute that is dissolved, you know in water. Okay, so and this effect is known as double diffusion. And since there are two diffusivities involved, that's why this problem is called as a double diffusion problem in instability. Okay, one classical example is the seawater that we see at when we visit a beach, or when we go to visit a sea, we see that the seawater on the top have salt in it, have dissolved salt in them, and that's obvious, right? But why the salt doesn't settles down? The reason is that it receives heat constantly from the sun, which means it warms the top surface of the, it warms the top surface of the sea. And that's the reason why it decreases its density, and that's precisely, the reason why, it so the salt doesn't, always settle down at the surface of the ocean, even though a mixture of salt and water is more denser than pure water that we have present. Okay, so this is where we see a classical example. But sometimes there can be cases where, salt can start moving from the top and comes, and so it can forms like, so basically salt from the top can, come towards the bottom if there is an interplay of the or interplay, of, so basically it just boils down between, the thermal diffusivities and the molecular diffusivities that you calculate. And there is a certain, ratio beyond which, instabilities kicks in through double diffusion. That's the idea, that take place in ocean. Okay, well, so that's how, gravity, I think things are clear. That's how gravity, determines or, plays a role in creating instabilities. हेलो. हाँ हाँ, मैं 5:30 बजे आ रहा हूँ भैया. हाँ हाँ. Okay, and I hope this is clear. And one of the mechanisms by which, the heat from the sun's core reaches its surface before it being radiated is by Rayleigh-Bénard convection. Okay, so this is one classic example of Rayleigh-Bénard convection. So maybe I can write that heat from the sun's core. See, the reaction is happening inside. So I believe you know that the fusion reaction is happening inside the core, and the heat from the core comes to the surface by Rayleigh-Bénard convection in sun. Okay, because the plasma there is actually unstable in nature. Okay, so the heat from the sun's core reach the surface by Rayleigh-Bénard convection. So this is one example. Okay, where we see Rayleigh-Bénard convection. And the other classical example is this, like heating a pot of water, basically. That's one classical example of Rayleigh-Bénard convection. By the way, this is not natural convection. You should not confuse Rayleigh-Bénard convection with natural convection, okay? Because this is kind of an instability that we are trying to study. Okay, so some other instabilities then. So there can be instabilities due to electric field as well. So there can be instabilities due to electric field as well. Okay, and such kind of instabilities are known as electrohydrodynamic instabilities. Okay, there can be instabilities due to magnetic field as well. And these instabilities are known as magnetohydrodynamic instabilities. Okay, and one of the reasons for the formation of Earth's magnetic field is due to this instability. Okay, so this instability is one of the reason. I mean, it's not the reason, but it's one of the reason for the generation of Earth's magnetic field. Okay, moving on. So this is how, body forces like gravity, electric field, magnetic field can cause, instability. There is also one very classical type of instability. This is known as a Rayleigh-Taylor instability. This is also something that falls under body forces. So there is an instability known as Rayleigh-Taylor instability. So this instability occurs, when, let's say, we have a beaker, and we put in, so basically if we put in, so in the beaker, if we, if basically we have two fluids, let's say of densities rho 1 and rho 2. And if rho 1 is greater than rho 2, see, if rho 1 is less than rho 2, it's a stable system, we know that. But however, if rho 1 is greater than rho 2, it is obvious that a fluid element which have a lesser density will try to move up, and this will be filled by the fluid with a heavier element. Okay, so these instabilities, so if you put a heavier fluid on top of a lighter fluid, the instability that get kicks in is known as Rayleigh-Taylor instability. Okay, all right. So these are the instabilities that occur due to body forces. Okay, for instance, gravity, electric field, magnetic fields, and things like that. Body forces having these these kind of descriptions. So instabilities can also kick in due to other effects. For example, interfacial effects can also kick in instability. For example, surface tension, one of the classical interfacial effects is by surface tension. So surface tension, can cause instabilities. It is a myth that surface tension always stabilizes an interface. This is a myth. In fact, there is a very famous instability known as the Rayleigh-Plateau instability, and this is something that so this is something, this Rayleigh-Plateau instability we have seen always in our day-to-day life, although we don't understand that this is Rayleigh-Plateau instability. See, if we open the tap of our kitchen sink or of our bathroom, we know that initially, the jet, there is a steady jet, and after that the jet basically breaks down. Okay, that breaks down of the jet is not due to gravity, but it is due to surface tension. Okay, and that instability is actually known as Rayleigh-Plateau instability. Okay, and sometimes they are also known as capillary instabilities. So that's a classical example of surface tension destabilizing a surface. And in fact, you can show that the breakdown length of the jet, for example, if you have two fluids of different viscosities, you can show that the breakdown length after which the jet basically breaks up, that is different, and it is actually very sensitive to the viscosity of the fluids. Okay, in fact, a fluid with a higher viscosity will have a greater length, will have a greater breakdown length with respect to the fluid with a lower viscosity. For example, if you take water and glycerol, water will break down more, water will break down more faster, or the breakdown length is less with compared to glycerol. You can do this experiment at your home itself. When you have two beakers, open the tap, fill one with water, fill one with glycerol, make the flow rate almost same, because the flow rate needs to be constant if you want to compare the breakdown length, and you will see that water will break up more faster with respect to glycerol. Okay, and in fact you can prove this analytically using linear stability. So there is it's little complicated with the problems that we have solved, because here you need to use something known as the kinematic boundary condition and the normal stress balance and the tangential stress balance, because you have an interface that is coming into the picture. But you can prove analytically using linear stability analysis in the regime of linear stability analysis and using normal modes, that and in fact you can show that highly viscous fluid have less breakdown length, sorry, have more breakdown length than low viscous fluid in Rayleigh-Plateau instability or capillary instability. Okay, so this is one example where surface tension actually destabilizes interface, and we call this instability as Rayleigh-Plateau instability. Okay, and sometimes they are also known, it is also known by the name capillary instability. Okay, now there is also one more kind of instabilities that arises from interfacial effects and from surface tension, is sometimes known as the Marangoni instability, and this occurs due to surface tension gradients. We all know that that's the Marangoni, it's related to the Marangoni stresses, so it occurs due to surface tension gradient. Okay, and usually you see, so this Rayleigh-Bénard convection is usually accompanied by Marangoni instability, because the fluid, when it moves up, the fluid molecule, when it moves up, it actually sees a surface tension gradient. Because of the difference in temperature, it creates a surface tension gradient along the interface, and then it basically comes towards the solid side, and then it moves down. Okay, so usually Rayleigh-Bénard convection and Marangoni instabilities, come hand in hand. For example, that that boiling example is a classical example of having Rayleigh-Bénard convection and Marangoni instabilities together. Okay. Now the third point is inertia can also cause instabilities. For example, the term v dot grad v. This is the problematic term, as we all know, because this is non-linear and it corresponds to inertia. So so inertia can also, so for instance, this term v dot grad v, this is a highly non-linear term, okay, and this term can cause instabilities in fluid, okay, because it's a non-linear term, so we know that this is going to create some problem, and inertia itself can be a source of instability in fluid systems, okay. Now you can see instabilities in porous media as well. And so the instability in porous media, one of the very famous instabilities is known as Safman-Taylor instability. Okay. Now, sometimes this Safman-Taylor instability is commonly known as viscous fingering. So what it means is, the idea is very simple. So you know that in porous media, so what happens is, if you zoom in into the pore scale, you know that there are solids, okay, in the region, and your fluid basically moves through, so these are known as pores, and your fluid basically moves through these pores. Okay, now it happens that in porous media, if a fluid which is having a less viscosity, let's say the viscosity of this fluid is 1, it basically tries to penetrate a fluid, let's say, of a viscosity mu2, where mu2 is greater than mu1. What you see is, you see certain patterns like this. So this fluid comes, and then it sees a fluid which is having a greater viscosity, which means that this fluid basically tries to the penetrate through the highly viscous fluid to the more viscous fluid, and then you see patterns something like this. Okay, so these patterns, that the fluid is with the lesser viscosity, when it tries to penetrate into the more viscous fluid, these patterns are known as fingering patterns, and the instability that kicks in, this is known as the Safman-Taylor instability. Okay, and this is also one of the so in research, this is one of the most studied instability problems in porous media research, that this Safman-Taylor instabilities. Okay, you can also have instabilities because of centrifugal forces. For example, if you remember the Taylor-Kuit flow problem, there were two cylinders, if you remember, and the problem was like, these two cylinders were rotating about their axis. They are basically rotating about their axis with some angular velocities omega 2 and omega 1. Now when the rotational speeds of the cylinders are, and remember, we had a fluid that is inside the annulus of these two cylinders. Okay, we had a fluid that was inside. So this was the example that we solved in our initial, when we are trying to understand the Navier-Stokes equation in the RZ, or in the cylindrical coordinate. This is something that we solved. I believe you guys have remembered this. Okay, now if the rotational speeds of the cylinder, that is omega 1 and omega 2, if their magnitude exceeds a certain value, let's say omega c, then instability kicks in, and the instability that follows because of this is known as Taylor-Kuit instability. Okay, so this is instability due to centrifugal forces, and I believe you can understand. Finally, there is also one very classical instability, which we call it as the Kelvin-Helmholtz instability, or the KH instability. It happens, this Kelvin-Helmholtz instability happens, and also you can have analytical solutions to Kelvin-Helmholtz instability. It happens when there is a lateral movement of two fluids with different velocity. For example, if I have a fluid, let's say, which is which is above a fluid. Let's say this, its density is rho 1, its density is rho 2. Okay, and for this, let's say we are considering rho 1, to be less than rho 2, which means the system is otherwise stable. Okay, and then if I give this fluid a motion in some direction, which maybe, let's say, the x direction, and the motion of this fluid which is below is not same but of different magnitude, whereas you can assume that the fluids moves with uniform velocity, for instance u1 and u2 along ex, these are the base states. And if there is a difference, between u1 and u2, this difference, you understand, there is a velocity, there is a shear that is caused at the interface of these two fluids because of the change in velocity. Okay, and this can actually cause, the interface to actually deform. This can cause the interface to deform, and you can show that this is the, and you can, and I believe that there is then an instability that kicks in. Okay, so the relative motion of two fluids along a particular direction can cause that. So basically it can cause an instability, and this instability is known as Kelvin-Helmholtz instability. Okay, and in fact you can do a very nice analytical estimation of kh instability, like using what to say, the the linear in the regime of linear stability analysis, and using normal modes, you can find analytical solutions for the corresponding eigenvalue eigenfunction pairs that we did for Kelvin-Helmholtz instability as well. But due to the interest of time, and since I hope you understand that since it involves an interface, it actually requires two more boundary conditions, which is known as the kinematic condition. For Kelvin-Helmholtz instability, it requires the kinematic condition and something known as the normal stress balance. So we'll not look into the details of this, but these are the two more boundary conditions that you need to use when you are trying to assess the instabilities of instabilities at the fluid-fluid interface. Okay, and that makes it a little bit complicated to the otherwise simple cases of parallel flows and like that. That's the reason why I don't specifically want to discuss them here in this class. Okay, so these are some plethora of instabilities that we saw, that is very interesting, and it is very, very common. For example, the capillary instability or the Rayleigh plateau instability, we witness it every day in our life, but we might not know that this is an instability that kicks in, or we might think that it's gravity which is causing the instability, but it is not. It is actually surface tension which is destabilizing the interface and causes the breakdown of jets. On the other hand, this Kelvin-Helmholtz instability is also seen, for example, certain cloud patterns in the sky. If you Google it, if you Google the name Kelvin-Helmholtz instability, one of the pictures that you see in the web are certain cloud patterns, and these are sometimes seen in the sky. And this cloud and the formation of these cloud patterns, they can be explained by Kelvin-Helmholtz instability. Formation of ocean waves on the surface of the ocean, they can also be sometimes explained by Kelvin-Helmholtz instability. Okay, uh, Rayleigh-Bénard convection, a pot of rice boiling is a classical example of Rayleigh-Bénard convection. And of course, when there is motion of two cylinders, we also looked at there's an instability that comes in, which is known as Taylor-Kuet instability. And so these are some various instability that can be caused from various sources, and this is how perturbation kicks in a fluid system. So I believe the objective of the studies is clear, although we didn't get much time to explore much on hydrodynamic instabilities. But I think the motivation is clear, that why there is so much time and effort that is spent to understand instabilities in fluid systems. Okay, so with this, I stop the discussion on you know on uh, on instabilities, and this happens to be the last you know the last discussion of this course. And what we'll do is, first of all, I'll wait for a couple of minutes, and then in the remaining 10-15 minutes, what we'll do is we'll do a very quick recap of the things that we have learned. And that's it. Then if there are any questions, I'll be happy to take the questions. If not, we will formally end the discussion hour of this course. But in the meantime, I'll just take a quick break, and like, if you have any questions, you can. Okay, but I believe that the motivation behind studying hydrodynamic instability is clear from the various examples that we saw. I mean, these are some examples uh, that we witnessed in everyday life where we see instability that kicks in. Actually, I should have covered this before, starting instability on parallel flows, but yeah, because this then establishes the motivation for studying that. Because otherwise, it doesn't become very clear that why we are actually studying it, because it's just some very pesky maths that we do, because the maths is not so easy here as we saw. I mean, it's very long. It's yeah, you need to be very strong analytically to solve this problem. But yeah, the reward is great, basically. Okay, so you can do a quick recap, but maybe I'll come in 2 minutes, and then we will do a very quick recap about the course, and then we'll call it a day. I'll come in 2 minutes. Okay, so let's then do a quick recap of the things that we learned, and I hope then it will be useful for you in the coming exams as well. So we started off this course by, looking into the very, very fundamental aspect of Reynolds transport theorem. We tried to apply Reynolds transport theorem into calculating certain fundamental quantities. For example, like we applied conservation of mass to evaluate the velocity of a fluid, to evaluate the velocity field, let's say, of a fluid that is passing through a cross section, and or using that to estimate, let's say, the height that an inflowing fluid inside a tank can reach. Okay, uh, using the Reynolds transport theorem or the mass balance. We've also applied Reynolds transport theorem for momentum conservation as well, which from which we calculated the net force. We calculated forces on particular directions, and after that, what we did is we looked into the definitions of stream function, uh, and the use of stream function, and the regime in which you can actually apply the approach of stream function. Okay, and the basic definitions of fluid kinematics, for instance, material derivatives, and like total derivative, and trying to understand the basic gap, sorry, the basic difference, I should say, between the Eulerian and the Lagrangian approach. Okay. Thereafter, we looked into very special, cases of to the much celebrated Navier-Stokes equation. For example, we looked into, rectilinear, and flows taking place in planar geometries, for instance, Couette flow, or plane parabolic flows, and things like that. We solved. So basically, what we did is we actually solved the Navier-Stokes equation, and in these simple cases, we saw that the very complicated Navier-Stokes equation, which is actually, it's a quasi-linear PDE. It's a quasi-linear PDE, but we saw that under certain assumptions, you can actually get analytical solutions to the Navier-Stokes equation, and the very simplistic cases are the cases like Couette flow or plane parabolic flow, or and then increasing a little bit of complexity in the paradigm, we looked into like how flows take place through cylindrical geometries by using the cylindrical coordinates and the cylindrical versions of the Navier-Stokes equation in the r theta and z direction. Okay. Then we saw that. So what we saw is like, okay, but before that, we also looked into a very important aspect, which is known as non-dimensionalization. Although it was not discussed directly in the lecture series, but we saw that if we non-dimensionalize a system, it it basically the algebra becomes very much easy, even though you need to spend some time in choosing the characteristic variables and defining the non-dimensional counterparts of the dimensional variables. But we saw that it has enormous applications in trying to understand the physics of a certain problem. For example, if I solve a problem non-dimensionally, we saw that we don't encounter physical properties in the answer. For example, we don't encounter properties like mu, rho, which are physical properties. Rather, we encounter properties like non-dimensional numbers. So this have twofold advantage. One, it makes the analysis generic because it is not just limited to a certain fluid. You basically need to have a choice of the Reynolds number to basically know the range of solutions that you are trying to apply for, that you are trying to do the analysis for. The second advantage is that you don't, since we are non-dimensionalizing the variables, generally the variables in the equations remains order one, because we are writing a dimensional variable by divide. So you're writing a non-dimensional variable which is equal to a dimensional variable divided by a characteristic variable, and the characteristic variable is kind of like the ballpark figure of the dimensional variable, which means that the non-dimensional variables remain order one. So then the analysis becomes simplified because we don't actually need to think about the absolute magnitudes of the variables here, because we know that it's a non-dimensional expression. So the non-dimensional version, for example, del u by del y, we know that del u by del y is going to scale as order one. Okay, in the, let's say, the non-dimensionalized version of the continuity equation. Sorry, del u by del x, I should say. Okay, now after learning non-dimensional analysis, we kind of looked into a more advanced version of applying the or using the Navier-Stokes equations by adding some complexity there. For example, now we saw that the Navier-Stokes equations, which were ODEs in simple cases of, let's say, Couette flows, or Hagen-Poiseuille flow, or plane Poiseuille flow, now they are PDEs, where we looked into problems like the Stokes first problem, the Stokes second problem, or like motion of a fluid that is flowing through a confinement, which is let's say the motion of a fluid flowing through a square duct. And there we saw that the essential difference was that the equations which we are solving, that's the Navier-Stokes equation, of course, they were PDEs instead of being ODEs. So PDEs is just a different ball game than ODEs. Okay, it's very, so first of all, solving PDEs is not as simple as solving ODEs, as we have seen. And we saw that a single PDE can have, so I think we didn't prove this, but we got some glimpse that a sim you know a, I mean, the fact that it is a PDE, you cannot say that a PDE will always have this particular sort of solution. I mean, I think we have discussed some bit in the cases where we are learning these problems. Okay, which means the solution of a PDE is actually very sensitive to the problem that you are trying to solve for. And the examples that we saw is, as I said, is the Stokes first problem, Stokes second problem. Okay, Stokes first problem is little different because we applied the similarity variable where we essentially converted the PDE into an ODE, but in principle we are solving a PDE only here. Okay, we just use the similarity variable to convert the PDE into an ODE in eta. I think that's what we did. And in the Stokes for second problem, remember where there was a plate that was oscillating back and forth, and as a result, the fluid was also oscillating back and forth with some phase lag. We considered the solution to be of, let's say, if you remember, it is some real part of, let's say, u hat of y e power it. That's how we solved it. Thereafter, uh, look, but the point is here also we could actually find analytical solutions to the Navier-Stokes equation. Okay, and I believe so. I don't know if you guys remember this or not, but I think this is where we actually did this. I think it's week 4. Yes, it's basically this week. Okay. So one more example that we did of this form is that like an oscillating pressure gradient flow, or in a, an oscillating pressure gradient, when there's an oscillating pressure gradient imposed in a cylindrical flow, we saw that there was a time perspective that also comes into the Navier-Stokes equation, and in fact the governing equation there was also in PD. Okay, so this is one. Yeah, that's the oscillating flow in a cylindrical pipe, and this is something that we solve for. Okay. Okay, let's see then what did we do. Yeah, so this problem is like that is flow through a duct. This is something that we discussed. And then what did we do? Yeah, then then what we did is we now moved into solving 2D problems. For example, we solved a problem where there was a cylinder that was rotating with a given angular velocity. Also, there was a radial suction that is taking place through its surface at r equal to a or r equal to 1 non-dimensionally. So this essentially was a 2D problem that we solved, and we saw that instead of having velocity field in one direction here, we had two velocity fields, but the velocity field like u r and u theta, they were just dependent on r. Okay, so we solved. I mean, we need to use the Navier-Stokes equation in r and theta direction to come into a solution of this problem, and then we discussed things like circulation and finding and the regime where we said that when Reynolds number is less than 1, we can actually find the analytical solution to this problem corresponding to the boundary condition. Okay. Okay, what we then did is we then entered into a different regime of flows which are known as creeping flows. Okay, where we saw that we can basically use the concept of linearity to solve this problem, because we saw that in creeping flows the Reynolds number was tending to 0, which means that the inertia term, which is del v del t plus v dot grad v, that term basically goes to 0, which means our governing equations, which were quasi-linear in nature when we had the inertia term, now boils down to be a linear equation, although it was a PD. Which means one of the consequences that we saw is that we can use the method of principle of superposition. Okay, so we saw that, for example, we saw that a rotating particle, okay, in a shear flow, it doesn't generate any lift. Okay, and we saw that we can break that problem into simpler problems, and we saw that the individual lift force in all these in all these broken problems, or I should say in all these individual problems are 0, which means that if you add the lift, because the governing equations are linear, if you add the lift force, the lift force simply comes out to be equal to 0, again owing to the linearity of the Stokes flow equation. Thereafter, what we did is, as a prototypical example, we looked into the motion of a sphere that is moving through a fluid which is actuated by a background parabolic flow, and we use something known as the hydrodynamic force free condition to derive the steady state velocity of the sphere. Okay, and we use the theorem, if you remember, which says that, so basically what we did is like we solved the biharmonic equation in the stream function. Okay, and we saw that of course the stream function satisfied the fourth order equation, and the solutions can be written as a series solution of the coefficients a and b and cn's and dn's, where an's and bn's can be obtained from the boundary condition at at far field, while bn's and cn's can be evaluated from the boundary conditions on the interface. And we saw that the force precondition says that the net force on the sphere is proportional to the constant c1. So it just suffices to evaluate the constant c1, and then if we want to calculate the velocity of the sphere, we just equate F, the net force to be equal to 0, which gives us an expression for C1. Okay, remember this theorem that we use, that the net force is proportional to C1. This is actually applicable in the regime of creeping flows. Number one, the object, even though it's not a sphere, it is applicable for any object having an axis of symmetry. Okay, that's number two. And of course, number three is that since it's an axisymmetric object, you are basically using stream function. Okay, after that, what we did is we went on to a little bit of boundary layer analysis. Okay, where we looked into two approaches: the von Karman momentum integral approach of evaluating the boundary layer thickness delta, and things like displacement thickness, momentum thickness, definition, the physical interpretation of displacement thickness, momentum thickness, and things like that. And then also we looked into a flavor of Blasius's solution as well, by trying to evaluate something called as the characteristic variable of the stream function, and there we saw some glimpses of Blasius's solution as well. Okay, and we also looked into the case when there can be a pressure gradient that is possible, which if the pressure gradient is adverse, we saw that there is flow separation that can present, and the necessary condition that we saw is that there should be an inflection point in the velocity profile. Okay, now after boundary layer analysis, we moved on to the last module of the course, which is hydrodynamic stabilities. Okay, and as we saw today, there is immense motivation to study to study stabilities in fluid flow or in hydrodynamic systems. But the problem that we solved was a simplistic problem of a parallel flow, where instability is kicked in, and we were looking into the inviscid regime, where we actually derived an expression, an ODE, which governs the eigenvalue eigenfunction of the stream function that we write in terms of normal mode. And typically we saw that the consequence of that, by the way, the equation that we derived, this is known as the Rayleigh stability equation, and we saw certain consequences of using the Rayleigh stability equation and how can it predict the instabilities in fluid flow systems. And and thereafter we looked into different sources of instabilities, although we didn't perform any analytical work on that, or like didn't derive anything, but we looked into physical systems where and how perturbations can get kicked in and cause instabilities. Okay, for example, like Rayleigh-Bénard convection, Rayleigh-Taylor instability, Kelvin-Helmholtz instability, uh, and things like Safman-Taylor instabilities, and numerous other examples. Okay, and this is where we formally end. So these are all the notes. I have shared these notes. I'll share the week 11, week 12, and this week's 13 notes in the course website as well. I have already shared the recordings up to the previous class. I will also share the recording for this class as well. And yeah, that's it. Then this is where we end it. I hope you have learned something from these sessions, which I believe would be helpful in general in the overall objective of learning something out from this course. And also I'm confident that they will also help you in preparing for your exams that are coming for this course. Okay, so this is all from my side. If you have any questions, you can I'm here for the next, let's say, couple of minutes. If there are any questions or suggestions, you can ask, or yeah, like as I said, feel free if you have any doubts, kindly let me know through the discussion forum of the course, and I'll be happy to address it. Okay, if not, I'll share all the recordings as of now in the course website. You can go through them, and I just wish you all the best for your exams. I don't exactly know the date, but yeah, whoever is just sitting for the exams, all the best from my end, and that's it. So maybe I'll be here for a couple of minutes, just and then we'll call it a day.